All right, so this is the last lecture on the interaction charged particle with matter. So last time we talked about the quantity used to describe the interaction charged particle with matter, which is the stopping power. And we use the stopping power to describe the loss of kinetic energy per unit length of the instant charged particle. And typical behavior of the stopping power, let me redraw that again, has a this 1 over t shape. Okay, so usually we plot the stopping power normalized by the density of the material, 1 over rho. So in a very wide energy range, the stopping power is inverse proportional to V square, or the kinetic energy square. Then beyond certain energy cutoff, and begin to see relativistic effect, and this curve is going to turn back up a little bit at the high energy end. And at the low energy end, when the charged particles, the speed becomes really, really slow, then it's going to absorb the electrons from the material, capture the electrons. So that it's going to reduce the stopping power. The typical shape of the stopping power looks like this. Okay, and for this stopping power, it's related to the ionization process of material. During this process, the energy transfer from the charged particle to the electrons, and the electrons get kicked out of the atom, and so the material become ionized. So oftentimes also call this process as the ionization loss. So right here. Ionization loss. Okay, this refers to the mechanism for the loss of energy of the instant charged particle is due to ionization. So there are two additional ways for the charged particles to lose energy. One is Bremsstrahlung radiation, the other is Cherenkov radiation. Let's talk about them now. So first, Bremsstrahlung radiation. So this is something we had already encountered a couple of times from the beginning of the semester and in the middle of the semester. So Bremsstrahlung radiation refers to the electromagnetic radiation generated by a moving charged particle. So in classical electrodynamics, we know that the electric field that is get attached to a charged particle can be detached from the charged particle if charged particle undergoes some acceleration. Okay, so the radiation power is described by the so-called Larmor formula. If you have learned electrodynamics or some intermediate level electromagnetism, you might have heard of that, but if not, that is still okay. So the only result we need is this Larmor formula. So the radiation, electromagnetic radiation power generated by the moving charged particle is described this way. It's mu naught times q squared times a squared divided by 6 pi c. Okay? So mu naught is a constant, and c is the speed of light. So q is the charge of the charged particle, and a is acceleration. The important two parameters is charge and acceleration. Okay. So the radiation power is proportional charge square and the acceleration square. So normally, this is just electromagnetic radiation But if the energy of kinetic energy or the speed of the charged particle it's very high, and then this Brownstorm radiation will become important. If you take a look at the power of the radiation, by the way, this radiation is given out in the form of electromagnetic wave. And this electromagnetic wave can cover very wide frequency range. So the Brownstorm radiation oftentimes refers to when this radiation becomes very important. So in the case that when the radiation falls into like X-ray range, and we call them Brownstorm radiation. So using this Larmor's formula, we don't have to do a rigorous calculation, but if you take a look at charge dependence, acceleration dependence, so that means if you want to describe the loss of kinetic energy of the charged particle, the stopping power minus dt over dx of the charged particle due to the Brownstorm radiation, so we'll know the stopping power for this Brownstorm radiation is going to be proportional to the charge square and the acceleration square. So the charge of the particle is described by the small z, okay? So small z square. That's the first term. And the acceleration will be proportional to the force between the charged particle and the material and divided by the mass. So the force between the charged particle and material is Coulombic. So and the force will be proportional to small z times the capital Z. Okay, and this is used to describe the interaction between the charged particle and the nucleus through the Coulomb interaction. Okay. Of course, this process can also happen when the charged particle is interacting with the electrons. In that case, we're going to replace this this capital Z by just one electron, so just E, and there will be no capital Z dependence. And you'll see, because of the square dependence, so the interaction between the charged particle and the nucleus is much more significant than the interaction with the electrons. Okay. So the force is going to be proportional to the product of the two charges and the constant. Let's forget about the constant, and then inverse the distance. But we don't have a fixed distance here, so we don't have to consider that either. So the force will be basic proportional to z, small z, and times capital Z. And then divided by the mass. So that will be the acceleration. Okay. If you collected this few terms to be small z squared times capital Z divided by mass and then square. Okay. So if you take a look at the stopping power, we'll see the Brownstorm radiation will be important for, so this is going to be important for high Z material. Okay, because the stopping power is proportional to Z squared. So for high Z materials, oftentimes metals, so Brownstorm radiation will happen more likely in the metal or in high Z materials. That's number one. And number two, it's going to be important for small mass. If the mass of the instant charged particle is small, then we can have more Brownstorm radiation. So what charged particle is small, like electrons and positrons, beta plus. Okay. So with this very cool derivation, we'll see the Brownian relation, since it is related to the slowing down process of the charged particle, more specifically the acceleration squared, and normalized by the since acceleration is inverse proportional to the mass. So overall, the stopping power due to the Brownian radiation will be inverse proportional to the mass squared. Because this combination dependence of both capital Z, the charge of material, and the mass of charged particle, in reality, this Brownian radiation is not going to be important for like a heavy charged particle. Remember, at the beginning of this part of class, we mentioned that there are some subtle differences between the behavior of heavy versus light charged particles. For heavy charged particles, even proton, then the mass will be much larger, more than 2,000 times, about 2,000 times larger than the mass of an electron. Then you take the square of that, that's like a million, like a few million times smaller than the effect of the electron. So this Brownian radiation normally it's only important for like those light charged particles, electrons and positrons. So when you send electron beams, or positrons the same thing, or send electron beams to materials, then those electrons will get slowed down. And because of the interaction between the electron and the nucleus, and the electron can get slowed down very quickly, leading to a very large acceleration, then the energy is going to be released in the form of an electromagnetic wave. And the frequency of that electromagnetic wave can even fall into the X-ray range. In fact, that is one way for us to generate an X-ray beam. So, but if you send the electron beams towards, like say, a metal, and when the electrons enters the metal, they get slowed down very rapidly, and the energy is released in the form of X-ray. Okay. And for heavy charged particle, this effect is much less. In fact, oftentimes it is negligible. So this Brownian radiation is important, only important for light charged particles like electrons and high Z materials. Okay. Compared to the above figure, the stopping power due to ionization loss. So for this stopping power, this is due to the Brownian radiation. It is radiation. We call this loss of energy to be the radiation loss. Okay. So when we send in light charged particles like electrons to the materials, we have a combination of both. So the electron can interact with the electrons inside the material and cause ionization of the material. And stopping power is described by this figure above. At the same time, the electron can also lose energy through this Brownian radiation process. And that portion of stopping power compared to ionization loss, we can put it in the same figure in this intermediate range, will be something like this. It's going to be more and more important at high energy. Of course, it's still less than the ionization loss. So we call this as the radiation loss. Okay. So that's the comparison between the two. So lastly, is the Cherenkov radiation. So Cherenkov radiation refers to the radiation generated by a moving charged particle again, not with any acceleration, different from the Browns-Strong radiation. Browns-Strong radiation only happens when there's acceleration of the charged particle. The Cherenkov radiation refers to radiation generated by a moving charged particle with a speed more than the speed of light inside the material. Okay, so c is the speed of light in vacuum, and divided by the n is the refraction index. So n is the refraction index. Usually, well, it is more than one, like 1 point something, usually like 1.2, 1.3, 1.5. So when light travels like in certain media, let's say water, the speed of light in water will be less than speed of light in vacuum. Okay, so c divided by n will be the speed of light in the media. Okay, for example, let's say in water. So this is not contradictory to the relativity. So the moving charged particles with any particle with the finite mass cannot travel more than speed of light in vacuum, but they can still travel faster than the speed of light inside that media. Of course, this only happens when the speed of charged particle is very high. So when this happens, so we're gonna have a phenomenon discovered by Cherenkov. That's why he won the Nobel Prize for this discovery. You know, it's named this phenomenon is named after him, called Cherenkov radiation. So when the charged particle is moving with a speed more than the speed of light of the media, then the front end of the wave generated by this moving charged particle is going to add up together. And so let's say if you have a charged particle moving with the speed of v faster than the speed of light in the media, then the wave front generated by these moving charged particles is also going to propagate. And then they can add up together and generate a radiation called the Cherenkov radiation. So the classical counterpart will be like this, the sonic boom. So if you have ever go to like an air show, so when the airplane travels of faster than speed of the sound, then it's going to cause condensation in air, and you can see those like clouds. So the Cherenkov radiation will be similar to that. So when the speed of the light, when the charged particle is moving faster than the speed of light, then this electromagnetic wave carried by the charged particle is going to interfere with each other and then create this Cherenkov radiation. And Cherenkov radiation, it doesn't represent a significant way for the charged particles to lose energy, because usually this radiation is weak, but they don't really fall into the X-ray range. They actually fall into the visible light range. So remember the energies of visible light versus the energy of X-ray. For X-ray, we talk about keV, tens of hundreds of keV. And visible light and the energy range is in the electron volt range. Like these are 3 order magnitude in difference. So the energy loss due to the Cherenkov radiation is actually pretty small compared to the other 2 mechanisms, the ionization of radiation. So we don't have to plot the stopping power. Stopping power meaning the loss of energy, the loss of kinetic energy charged particle is negligible due to the Cherenkov radiation. But on the other hand, this is interesting phenomenon you need to know, because of this radiation can fall into the visible light range, and we can see it. And this is, as a nuclear student, you should know that the color of a nuclear reactor pool is blue, and that is exactly due to this Cherenkov radiation. So the charged particles generated by the nuclear reaction, when they travel through water, if their speed, the charged particles and often generated by nuclear reactions oftentimes have a very high energy. So their speed can be easily faster than the speed of light in water. And when they travel through water, they are going to generate the Cherenkov radiation. And the color of the radiation is blue. Okay, so these are another two mechanisms for charged particle interaction with matter. So lastly, two things. Given the stopping power, what we can do. One is the so-called range. So all the moving charged particles, after they lose energy inside the materials, giving out energies either through like ionization or radiations, they're going to come to a complete stop in the end. So we may want to know how deep the charged particles can travel inside materials. And that quantity is described by the range. And we can compute this range R using the stopping power. Okay. How do we do that? So R will be the integral of dx. So distance from the surface of material to the inside of the material. And we want to integrate this from 0 to, of course, the final stop, range R. Well, we don't really know what is dx exactly, but we do know the stopping power. Then we can carry out this integral by doing dx over dt, that's the inverse of the stopping power, and integrate over t. So we don't know capital R, so we can integrate this from the initial kinetic energy T naught to 0 when the particle gets to a complete stop. If you rearrange this a little bit, so what we know is the stopping power. So we have a dt over dx. Okay, got the minus sign, the stopping power, and 1 over this will be the dx over dt. So we integrate over dt, and since we add the minus sign, we change the integral from 0 to t naught. Okay, so now we can plug in the stopping power and compute the range of a moving charged particle with the incident kinetic energy to be T naught. Here, T naught is the incident kinetic energy of the charged particle. Okay. So once again, we don't have to carry out these calculations rigorously. The important thing is to know the dependence of R. So if we use by this formula, and we know the stopping power is minus dt over dx is inverse proportional to v squared. So it's inverse proportional to the kinetic energy. Okay. So then what is R? So R will be the integral of from 0 to T naught. So it's 1 over this quantity. So it's T dt. It's proportional to this. So R is proportional to this. And this is T squared. Okay. So the range is proportional to the initial kinetic energy square. If you increase the initial kinetic energy to be twice, then the charged particle can get inside the materials like 4 times more, 4 times deeper. So this R as a function of T naught is usually what we call the energy or range energy relation. So let's come back in a little bit. So here, remember, minus dt over dx is proportional 1 over t. This only happens at like intermediate or low to medium energy range. If you remember the curve, like the very top curve here. So from the relative low intermediate energy range, and we have an inverse T dependence. For high energy, it's minus 1 over the stopping power minus dt over dx. It's not proportional to 1 over t. In fact, it's more or less a constant. So if you look at this region, like high energy range, this is more or less a constant. Okay. So if this stopping power is a constant, then what about R? Its range is going to be proportional to from 0 to T naught. Then the stopping power is constant, just 1 times dt. So this is just T naught. Okay. And this happens for high energy. So for high energy charged particles, the range is proportional to the kinetic energy. So in reality, this R as a function of T naught is somewhere between T naught and T naught squared. Okay, and you can measure that. And this is the important quantity. We call it range energy relation. Okay, so describes the charged particle with the initial kinetic energy T naught and how deep the charged particles can get inside the material. Okay. So related to this, we can plot the so-called Bragg curve. So Bragg curve, it's when we plot the stopping power not as a function of t. So previously we plot the stopping power minus dt over dx versus t, the kinetic energy of the instant particle. So now we can plot this as a function of x, so the depth of the material. Okay. So here I'm going to show you one actual experimental result. So x is with the unit of centimeter. There's 1, 2, 3, 4, and then here would be like 3, 2, 1. So 1, 2, 3 for the stopping power with the unit of MeV per centimeter. Okay. So this Bragg curve describes the stopping power as a function of the depth of the material. When we send in a charged particle, let's say an alpha particle, the core of the helium, with the kinetic energy of 5.49 MeV. If you send this charged particle, alpha particle in air, okay, it's a very, very light material, just air. Then initially, minus dt over dx, the stopping power is inverse proportional to the kinetic energy. So the initial kinetic energy of the charged particle is large, so this minus dt over dx is actually start from a small number. As the charged particle begins to lose energy and gets slowed down, the stopping power actually increase because of 1/t dependence. The stopping power starts with a small value and then increase. Okay. So then it reaches a maximum because eventually the particle is going to go to a complete stop. So when that happens, the stopping power all of a sudden drops to 0. Okay. So this is the so-called Bragg curve. It describes the stopping power as a function of the depth of the material. So initially, you see the stopping power is actually pretty small, even though the kinetic energy of the charged particle is high, and the stopping power is small. If you recall, why is that? That is the case? Because of the kinetic the stopping power is inverse proportional to kinetic energy. Further back, you know why that's the case is because stopping power or the loss of energy per unit length will be related to the time the particle spent in that unit length. So initially, the charged particle has a very high speed, then the time for the charged particle to interact with the electron is short. That's why it doesn't lose a lot of energy initially. Then when the charged particle gets slowed down, it can have more time to interact with the electron. And that causes the stopping power to increase dramatically. And then eventually it has to come to a complete stop. So they show the sharp drop. Okay. And the range here will be here. The capital R is the range when the charged particle reach a complete stop. So for highly charged particles, we have a very usually very well-defined range R. And that depends on the material and depending on the energy of the charged particle. And this could be useful for us to design some engineering applications. Because now if you send heavy charged particle towards certain material, if you can tune the incident charged particle energy based on the above range energy relation, if we know T naught, then we can control the range of R. So we can control, in other words, we control where do we want to deposit the energy. So this is the reason of an important radiation therapy technique by using a charged particle. So because the charged particle doesn't interact with material much from the surface, but a lot of energies are deposited around this peak location. So if I tune the charged particle energy so that the range will be in the range of maybe some tumor cells, and then a lot of energy will be deposited to the tumor and thus can be used to kill the tumor. Like the proton therapy made use of exactly this principle. Okay, so another way to plot this figure would be if you plot the intensity of the charged particle as a function of the depth. Okay, if you plot the intensity, let's say normalized by the initial intensity, okay, so as a function of depth x. Okay, so then initially we'll see the particles do not get removed from the beam until the charged particle reaches this range R. Then all of a sudden the intensity drops to 0. Okay, this is for alpha particle right here. So the behavior of light charged particles will be slightly different. The difference lies in these electrons do not have a well-defined range. So typical behavior of an electron will have a much broader drop off in this intensity. So for electrons, what we're gonna see is something like this. So much for electron, much wider range. This is because of the electron, it's much lighter. They can be influenced by the materials much more than the heavy charged particle. Now, if I draw a schematic figure, so like I said, this is the material, it's a bulk material. When we send in electron beams towards the material, then initially the electron is going to interact mainly with the electron inside the material, okay, and cause the ionization process. So and then let me draw a rough cutoff range. So in this region, the electrons is going to cause ionization of the material. Then when the energy of electrons gets smaller, their trajectory are going to be influenced by the nucleus positive charge. So then you see the trajectory of the electron will not be as well defined as the heavy charged particles. They are like wiggling, can even go back and forth. And this phenomenon is called straggling. Okay, just because of the mass of the electron, it's much shorter. And that is why if you plot this intensity figure on the left-hand side, and the range of the electron is actually pretty broad. Okay, in this two part, the first ionization is due to this ionization process is due to the interaction between the electron and the electron inside the material. So the slowing down of the electron is due to the electron. So in this process, we sometimes call it electronic stopping. So when I talk of stopping power, you can be more specific about what makes the particle to stop. So the initially is due to the electron, because it's the electronic stopping power. And then when the energy of electron becomes very, very small, and then become influenced by the charged particle, by the nucleus, then we call this process as this nuclear stopping. And for heavy charged particles, we don't really have much nuclear stopping. So the process dominated by the electronic stopping and no struggling process. Okay, and compared to the Bromstrom radiation, so Bromstrom radiation only happens, so that's not related to the ionization, that's due to the radiation. That only happens when the electron has a very high energy and this material has a high-Z material. So I'm not going to draw them on top of that. That's additional process happens for special material, for high-Z materials and for electron. Okay, so that is that be all I want to cover for this class. And at the very end, I want to give you one interesting and important example. And by putting both the photon, neutron, charged particles together, let's say if we have a 1 MeV radiation to 1 MeV radiation, it can be heavy charged particles, like say alpha particle, and can be light charged particles like electron, and can be photon. Okay, of course, it can also be neutron. And if we send these radiations in materials, if you send this to aluminum, okay, then what is going to happen? So for alpha, so for all these radiations with 1 MeV, with 1 MeV energy, So if you send this heavy charged particle, electron alpha particle in aluminum, then the alpha particle is going to cause ionization inside the material and then comes to a complete stop. So the range is actually very well defined. It's roughly 3 micrometer. Okay. So alpha particles do not get inside the materials very deeply, only micrometers. And for electrons with the same energy, then they can go to much deeper. So for electrons, actually this range, of course, is not very well defined. The average of range of electron will be like 1.8 millimeter. Okay. So notice the change of the unit from micrometer to millimeter. So electrons do not get very deep, but still much deeper than the highly charged particle, like alpha particle. And for photon, if you send in like 1 MeV photon towards materials, without calculation, we'll know that photon will get much deeper inside the material. And this process is described by the attenuation. So given attenuation coefficient, we can see, photon will always have some probability to get through to the half thickness. So we cannot describe the, so photon do not completely stop. So we can only define this kind of range based on the distance when the intensity of the photon beam gets lost by half. So the half thickness for 1 MeV photon in aluminum is in the centimeter range, like 4.2 centimeter. Okay. So if you compare the three of them, for heavy charged particle, light charged particle, and photon, and the range goes from micrometer to millimeter and to centimeter. So gammas can penetrate inside the materials much deeply. And for neutron, okay, so for neutron, I think, in fact, for neutron, it's better not to put it on the chart because the neutron interactions depends strongly on materials. And one material very special, which is the hydrogen. So whether you're sending the neutron beam toward hydrogen or others, then the behavior very different. In fact, in this example, aluminum, like a neutron, basically has 0 cross section. So for aluminum, in fact, for thermal neutron, but it's not thermal neutron, but for the thermal neutron, the cross section is almost 0. So aluminum is almost transparent to neutrons. So there's really no like half thickness. Neutrons can go through aluminum without seeing anything. They can go much deeper than gamma. And that is why for neutron facilities, we use aluminum to construct the instrument. Even though we use a very thick aluminum, then to neutron, they are just transparent. But on the other hand, if we replace the aluminum by like a hydrogen-containing material, like say water or some organic material like polymers, and hydrogen has a very large cross section, then you see neutrons will get scattered. And if you monitor the intensity at the direct geometry, then you can also describe that process by attenuation. Then for the bulk, I can give you a number for thermal neutron. If the thickness or if the material you have is water, then if you use like say 0.1 millimeter, 0.1 millimeter water, and the transmission of the neutron will be like 95%, something like that, 90-something%. Okay. So that's for 0.1 millimeter neutron, 0.1 millimeter water. If you increase the thickness to be 1 millimeter, then the attenuation of neutron will get dropped by a lot. But if it's aluminum, even if it's a few centimeters, then the transmission will still be very high, close to 100%. Okay. So that is why it's better now to put neutrons on the chart. So they depend much stronger than the materials. So, but for the other three, alpha particles, electrons, and gamma, for all of them with 1 MeV energies, you can estimate roughly how deep this charged particle, this radiation can go into. So that ranges from micrometers for heavy charged particles to millimeters for light charged particles to centimeters for photons. Okay, and this has a huge consequences. You know, it can tell us like if you want to shield those radiations, like what kind of materials do you want to use, and what kind of equipment do you want to use. You know, alpha particles, there's really no need to worry too much because they only get into like micrometer range. So normally, if you wear some like gloves, then they can already protect you from those alpha particles. And the electrons are slightly more difficult, and the photons are, of course, the most difficult to shield. So, so this is important for radiation shielding and health physics. Okay, so I think that's where I want to end this class, and I'm sure you're gonna learn more about this in many of the future classes in NPRE. Okay, thank you for the attention.
Thank you very much.